Agents fail when every memory is stored the same way. We'll separate semantic facts from episodic experiences, so retrieval returns what the next decision actually needs. You'll learn how the pieces fit into a workflow that stores memory by purpose and chooses focused context for decisions. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Flat memory makes agents noisy and slow. If every observation lives in the same pool, retrieval pulls irrelevant stuff. That bloats prompts, raises latency, and sometimes leaks outdated or sensitive values. The useful fix is simple. Store durable facts differently from one-off task traces, so the agent can pick the right context for the right problem. At a glance, semantic memory holds stable facts like user preferences or API keys that should persist. Episodic memory holds the step-by-step traces of past tasks, like last troubleshooting steps or partial outputs. Imagine a chat agent. Knowing a user's time zone is semantic. Remembering the exact error stack that happened 5 minutes ago is episodic. Separating these reduces prompt bloat and makes retrieval decisions precise. We will build a tiny pipeline that routes incoming messages into 2 buckets, promotes repeated traces into facts, finds the single best episode for a query, filters facts for safety and recency, and then assembles a small context for the agent. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need a cheap, visible storage policy that separates arrivals into 2 buckets. This snippet separates incoming memories into semantic facts and episodic task records. Undifferentiated memory forces every later retrieval to guess whether an item is a durable fact or a past event, which is exactly how stale traces sneak into prompts. The list comprehension splits items into semantic for stable user info and episodic for one-off task traces. There are no embeddings or ranking yet. The point is a cheap, auditable storage decision you can inspect. The printed sizes show the 2 buckets, so you can verify routing before you ever try to read memory. Now that we can route data, we need a promotion rule so repeated observations become durable facts rather than noise. This example promotes a repeated observation from task traces into semantic memory. A single episode can be noisy, so new traces stays episodic until counts shows the same fact appearing more than once. Counter gives a tiny, auditable promotion rule. Only facts with scene greater than or equal to 2 move into promoted. And semantic.extend records them as durable context. In production, this threshold is a policy knob, not a universal truth. Increasing it reduces accidental promotions, while decreasing it learns faster, but can memorize one-off behavior. The output shows 1 promotion and the new semantic size, making the memory write easy to monitor. With some durable facts available, we still need to pick the one episodic trace that best matches the current task, so the prompt stays focused. This code retrieves the most relevant episodic trace for the next task. Past task traces help only when they resemble what you're doing now. Dumping all of them into the prompt slows things down and invites irrelevant instructions. The loop turns each trace into words. Scores overlap with query, and keeps best task with best score. This tiny scoring routine is a teaching placeholder. A deployed app might swap in embeddings or a hybrid retriever, but the policy shape stays the same. The output names the chosen episode and its overlap score, which is your first debugging handle for retrieval quality. Episodic selection is helpful, but semantic facts need guardrails, so old or unsafe facts do not pollute decisions. This snippet filters semantic facts before they enter the prompt. Durable facts still need checks, because old addresses, leaked secrets, or policy-sensitive values can be worse than missing context. Facts carries the text, last seen date, and a safety flag. Safe facts keeps only items that are both allowed and no more than 30 days old, relative to today. Raising the 30-day window preserves more context but increases stale memory risk. Lowering it is safer, but may forget valid preferences sooner. The output shows how many facts survive and which one remains available for retrieval. Finally, we assemble a bounded, predictable context, so the LLM sees only the most useful pieces. This snippet assembles a bounded context from both memory types. The agent now has two independent retrieval paths. Semantic hits pulls a safe preference, while an episode hits ranks the most related task trace for the current query. The slices are explicit budgets, so a caller can cap cost and latency without changing the storage model. Words gives a small operational signal for prompt growth, which is useful in incident reviews when a context window suddenly bloats. The output shows one fact, one episode, and the resulting word count, giving a compact baseline for safer agent memory. In a real system, you map the single episode to the recent session logs, and the semantic facts to a light user profile store. That split keeps write simple and lets you swap retrieval strategies. For example, replace the episodic retriever with embeddings without touching how facts are written or promoted. Use this approach when your agent mixes long-lived user context with short task histories. It keeps prompts smaller, speeds retrieval, and limits stale or unsafe context. Try it when prompt bloat or irrelevant memory hurts accuracy. One caveat: your promotion rule is a policy decision and can overfit if you set the threshold too low. A practical next step is to tune the promotion threshold from seen greater than or equal to 2 to seen greater than or equal to 3, and then measure how many semantic items appear after 1 week of chat logs. That single knob will show whether the agent overpromotes noisy traces or learns stable preferences at the right pace. If practical AI engineering helps, subscribe and watch the AI engineering videos.